Okay, thank you guys. So we're going to start right now. Um, Thank you for coming, first of all. I'm gonna explain a bit who we are and what we do. So my name is Cristian Lungu. I'm a senior machine learning consultant and trainer. Maybe you've seen me at some other venues like Lungu, Big Data, Data Science, or Dev Talks. I also presented last year at Texylvania. I had a workshop on terrorists. How could you catch terrorists with machine learning and NLP? I worked in the past with several companies, and you can see them there. And currently, I'm the host of a machine learning workshop, or yeah, machine learning course, if you want to say it this way. You can find more information about that at my blog, and I'm going to post this presentation again on the blog, so you can find it there. Now, about the machine learning workshop. So this is a course which takes like 2 months. In total, there's like 20 hours of content. It's on after hours, so it's from 6:30 to 8:30, and it's held at the office in one of their conference rooms. It has some requirements, so if you want to attend, it's like you have to make a commitment of 8 hours per week for self-learning. So besides those 2 hours that you spend each week at the course, you have to spend 8 hours by yourself. Okay. Thank you. Okay, is it better? Yeah, so, okay. And you need 2 years of prior professional programming, because you can't, from my perspective, you can't really do machine learning if you don't know how to program. We are in the middle of the second edition of this machine learning track, and a new one will come, which is aimed at deep learning. And I'm going to answer this because usually people ask me, why should I join? We didn't invent anything there, so everything that you would learn, I didn't discover that. So you could find that as well online. The only thing that me and my colleagues can offer you is a learning environment, so some sort of support group, homeworks and personal feedback, and I find that when I learned machine learning, that lacked the most for me. There's also questions and answers that you can ask, so there's a two-way feedback communication going around, and there's the problem, which is seldom discussed, of how would you use a machine learning in production. So going from problem, what kind of data do you gather, how do you model that, how do you clean it, how do you debug it, and then how do you deploy that to production. So this is why, from my point of view, you might want to join. But coming back, so the topic for today is to talk about convolutions. And I know that at least this word sounds familiar to most of you here, because it's the backbone of most machine learning success stories that you've heard in the past decade. Initially, they were discovered in so there's like 20 or so years since they have been discovered by Yann LeCun. Yann LeCun, which is now the head of artificial intelligence research department at Facebook. And there's also been a big contribution by one Romanian fellow of ours who translated that to the GPU. So basically, he did a GPU implementation of convolutional neural networks. And I would say that these two combined made the success story of convolutions of what they are today. So as I said, convolutions are one of the main building blocks for image processing tasks, and you can find them in self-driving cars, like in Tesla, or in face tagging on Facebook, you all know Facebook, or in landmark detection, yeah, Google, spelled with one more O, or on Google, yeah. But intuitively, what's a convolution? I guess most of you have saw the movie Predator. Right? So if you remember, the alien in that movie had a capability of seeing an image through different kinds of perspectives, filters, infrared one and normal light one, and there's I don't know how many more. But basically, this is what the convolutional tries to achieve. It tries to get an image and tries to present it in several different filters or forms of representation. And then, yeah. So yeah, basically like in Predator. That's the intuition behind it. Taking an image and making it so transforming it into different ways of viewing it. Going a bit more into what this is. So let's assume that we define the word kernel. So a kernel, let's say it's a small matrix that has some interesting properties. So you want that kernel, that matrix, you want that to be applied on the image. And you apply it by let's say, so that kernel is applied to every patch of pixels one by one in a sliding window fashion. So you multiply, for example, these 9 values on top of 9 pixels here, and then 9 pixels on the right, and you go a little bit on the right as well until you pass the first line, and then you go back and you pass the second line again. So basically, you take this small kernel, and when you apply it on the input image, you get a feature map. That's what it's called. It's a feature map or a filter. So this is a way of viewing this image by applying the kernel on top of it, right? And now those numbers might mean nothing to you, and people spend decades on finding these kinds of numbers. So this kind of finding the best kernel is feature engineering, and you usually don't want to do this. Now, that's the main idea behind convolutions. So convolutions try to find these interesting kernels for you automatically from the data that you provided, right? So that's the basic, but that's the basic gist of it. You want to find all the kernels, all the interesting kernels that transpose your image into interesting ways of looking at that image. Now a bit going again into more details. As I've said in the beginning, that a kernel is, you should think of it as a sliding window. Yeah, so it detects certain patterns like a line and a corner, depending on what it does, on what those values in the kernel are. It can detect, in this instance, lines or edges, or it can detect different kinds of patterns. But it's basically a sliding window. It's basically a small patch that is slided across the image. So you can view it in this way. And mathematically what it's doing in the back end, it's taking this kernel and it's multiplying the respective pixels and then adding them up together to get a single number. So this kernel, like in this kernel, you have -1 times 3, and you have 0 times 0, and 1 times 1. So they're all added up, and you can see this computation done here. So it's -1 times 3 plus 0 times 0 plus 1 times 1. And you do this for all numbers, and then you have a result, which is minus 3. And that's the value that you insert into the end product, like the result of the filter, the result of applying this kernel on the original image. So you do this for this patch, for this large 3 by 3 matrix, and then you slide one position to the right, and you get this new matrix on which you compute the convolution, and you get a new number here, and the new number here, and the new number here, and slowly you start filling up this whole matrix. Now, I guess I can feel that there's a question of what's happening on these lines, on the edges. And we're going to talk about this edge case, because it's actually an edge case later on, yeah? Okay, so usually when you use a convolution, or actually when you use convolutional layers, you don't use only one convolution. You use a stack of them, one on top of the other. And the reason why you would want to do that is because, of course, the first convolutional layer would learn edges, how to distinguish between edges and small curvatures, let's say, and then this second layers. I mean, the second layer of convolution would learn to combine those small features like an edge on the left or an edge on the right and a small curvature into a more complex pattern, like let's say a triangle or a rectangle or a more complex shape. And going layer by layer, you just build up these features into more complex shapes. And I can show you this. So basically, this is the first layer of an image processing network. It learned only rudimentary shapes on the first layer. Okay, so some edges, some patterns of edges, and some form of transitioning from one color to the other. But when the next layer came and it combined all those kinds of representation, it combined them into a new form, and it's more complex, of course. So, sorry. And then going up again on the abstraction, it's able to compose complex images. Like this is a pattern of a honey hive, I guess, and some form of duck. Yeah. So this is another example where you have filters that detect edges. And up until now, I just presented some pictures, and that's it. And I'm guessing that you're not here to see pictures. So let's dig into some code. I'm going to talk about MNIST. I'm sure some of you would roll their eyes saying that, again, we're going to present again on MNIST, and MNIST is a fairly known data set. But bear with me, I mean, it's just for presentation. So for anyone that doesn't know what MNIST is, it's an old data set of images that contain handwritten characters. And it has been a database on which machine learning engineers compared their approaches for many decades. But yeah, so we're going to use MNIST as our example. Basically what we're going to do is we're going to load the MNIST, and you can see here that you have 16,000 examples of images that are 28 by 28, and they only have one color channel. So it's like they're gray images. And then you also have the labels for them, which is the correct number for each image. Each image has a correct label, a correct number that it should represent. And we have a split between these in this data set. We have 16,000 examples for training, and we have 10,000 examples for testing purposes. So let me show you how the data set looks. So this is 5, and the label for it is 5 and 0, 0, 4, 4, and 1, 9, 2. So you get the idea. Coming back to convolutions. So the simplest model, I'm going to use Keras, and it's not because Keras is the de facto standard or anything. So there's multiple ways in which you can implement convolutions, but it's easy to be understood and presented. So to get the idea behind what a convolution is and how it works, the API it's nice. So I'm going to use Keras for this purpose. So coming back, I was saying that convolutions can be in the most simplest way. They can be used as a single layer. So this is what I did here. So you have only the input. The input basically doesn't do anything. It's just it maps your data to some internal representation, a tensor that's going to be put on the GPU. So this layer doesn't do anything. Then you have the convolution, and then you have these two layers that are not really important. They're just saying I want 10 outputs. So transform all the convolutions that you have as a result of applying this filter, transform that into 10 values. Now let's explain a bit, or let's dig into it. What are those numbers? First of all, I was saying at the beginning that the convolution tries to express a single image into multiple ways of looking at it, so multiple filters. This is so the first number is basically how many numbers of filters, how many ways of looking into your number do you want? So in my instance, I said I want 20 types. I want you, the computer, to find 20 types of ways of representing each of my images. And then comes the kernel size. So so we were saying here that we have a 3 by 3 kernel. I was just showcasing you above a kernel which is 3 by 3. This is a 3 by 3 kernel. So I want only 3 by 3 kernels, and I want 20 of them. So I want 20 kernels of size 3 by 3. And then there's the activation and border mode. We're going to talk about border mode in a moment. The activation isn't really important. It's just a way of instead of saying I want a summation, I want to compute this sum. The activation says, okay, after you do the weighted sum, do something else with this value. Don't output directly -3. Pass that through an activation function, a function that transforms it a bit. But it's not really important. So, yeah, in this case, ReLU means maximum between 0 and your value. And if you apply 0 and -3, you get 0 in this instance. Okay. So coming back, so this is the simplest example where we have a single layer, and you want to present it into 20 different kinds of filter. And if we compile this model and if we fit it, I've just fitted this for you before, you can see that we end up with some accuracy. This is the accuracy here on the validation set of roughly 87%, which is good but not great. I mean, it's actually pretty bad for this kind of data set. But our goal is not actually, in this talk, is not actually to get the best accuracy out of it. It's just to understand what each parameter does and how it works. Okay, so let's use that model. So once we trained it, we can predict for let's say the first 10 examples from the training set, and then let's see what the actual correct results were. And we get a few errors, like we had 2 here, but we outputted 0. But basically, it's working, as I said. Now, the question is, we've trained the convolution. Can we inspect the model? Can we see what it learned? Can we see what those filters are? What are those outputs? And despite the misconception that usually you can't really inspect the neural network, you can't see what it has learned. That's largely inaccurate. So we have a way to inspect the values or the outputs of a filter. And what we're going to do, it's maybe more complex, and it defeats the purpose of this talk. But just to explain what you're going to see, we're going to take an image, and we're going to try to see we're going to try to generate an image that maximizes the outputs for a single filter. So we're going to try to express mathematically, try to find the image which maximizes the outputs of filter 1 and then the outputs of filter 2. So saying, which is the most interesting image for filter 0? Which is the most interesting image for filter 1? And by doing this, you get a sense of what each filter does. So I've written this code for you, and I'm not going to explain it because it takes some time. And these are the filters, the 20 filters that the single layer, the single convolutional layer learned. I guess you can understand that so you get the idea that some of them are edge detectors, vertical or horizontal ones. And there's some detectors or corners, and some of them are not that intuitive. Some of them might seem random. But keep in mind that these form of representation, when added up together, they express numbers. They can detect this is a 2 or this is a 5. But it's not that easy to see when you only have one convolution. So I was saying that convolution neural networks usually have more than one layer, one convolution layers. So this is one example. I mean, a proper way of using a network, of using multiple convolutions into a network. So what you see here is a sequential model. So it's a model that contains, so this is a deep learning model, so we're talking about deep learning from now on because we have multiple layers. If you ever wondered what deep learning is, it's multiple layers. So you have 3 convolutions stacked one on top of the other. First the first layer says, I want 7 types of filters. The second one says, I want 7 types of filters. And the last one says, I want only 5 types of filters. And again, I want to receive 10 values, 10 predictions, one of which I expect to be the maximum. I expect the correct value to have the maximum value of those 10. So we're going to train this. And after we've trained it, and I'm not doing the training right now because it takes some time, but I've trained this for you. So we're receiving, we now have an accuracy of 97%. 97% is way better than 89% that we had before. So it shows that it really works to have stacks of convolutions, one on top of the other. Now let's just use this. I mean, you have a model and you want to use it. And if we, again, predict the outputs and the expectation, I can't really see any errors in this example. So in the first 10 examples, all of the outputs are correct. But let's do this trick that we've seen before. Let's do it again. Let's try to see what the convolution learned, what one layer understood from the images. So if we're gonna inspect layer 1, which layer 1 means this layer, the middle one. So this is layer 0, this is layer 1, and this is layer 2. So if we inspect layer 1, these are the filters for it. Or better yet, if we use another library that's called SHAP, we can see a better representation of what each image has learned. So you can see that the activations for, when we give it an image of 2, we can see that the activation of the second, so these are 10 values, meaning that this is the prediction. If this would be red, this means so this is what's called an one-hot encoding. So you have 10 types of representations here, and only one of them should be high. And the high one means that's the correct answer. So it's not 0, it's not 1, it's 2. In this case, it's not 0, it's 1. So using SHAP, you can investigate what each filter is and what it learned, despite the general idea that you can't understand what the convolution does. Now, it's something interesting. When you look at, let's talk about the parameters here. So you see here that there's 70 parameters. So there's 70 weights that you can learn in order to generate these 7 filters. Does anyone has any idea of why there's 17? Where this 70 comes from? So there's obviously 7 types of filters, so it's 7 by 10. But the question now is what the 10 is, what 10 represents. What? Sorry? Not quite. So they're not the 10 values. They're actually, so the 10 is 9 plus 1. 1 is the bias value, and 9 is 3 by 3. So you have the matrix 3 by 3, and you have a bias value. So there's 10 weights, and then you have 7 times as much. Okay? And this is easy. I mean, this is the easiest case. But on the next layer, you have 448, and it's not that obvious. It's not that easy to compute as the previous example. 440 parameters means, of course, you have 7 layers again. So yeah, you have 7 times 64. Now the question is what that 64 means. 64 is again 63 plus 1. 1 is a bias, and you have 63 values. But those 63 values have to be applied on these 7 pixels. So you have 7 channels that you need to combine into a single form of representation. Okay? So the computation is this. So you have 7, so 448 is 7 filters, and each filter has a 3 by 3 matrix, and each pixel on that 3 by 3 matrix has 7 weights. And it has 7 weights because you have so you have seven stacked convolutions. So each pixel is actually an array of 7 values. You have 7 filters. Each pixel is represented in 7 different kinds of ways in time, let's say. Okay, so we have multiple filters. So that means all those 7 values for a single pixel need to be converted to a single value, as in the previous example where we have only one input, only one pixel. So the way you do it is you basically do a linear model where each pixel is multiplied by the weight. So each pixel, each of those 7 pixels has a corresponding weight, and those are the 7. So those are the 7 weights. Maybe it's too much for this time so for the hour that we are in, but yeah, sorry for being pedantic. So there's a reason why you have so many values of trainable parameters there. But I'm sorry to say that this is really important to understand that there's actually linear regressions happening between the filters. So you're doing linear regressions between filters, and then at the result of doing linear regression, when you end up with a single filter combined from every other 7 filters, then on top of that, and only on top of that, you do a convolution. So you only do the example that I just show you in the beginning. Okay, enough with how many weights and why. Let's talk about borders same. So I used at some point borders same. This is basically an edge case. So it's trying to fix an edge case in the way you compute. If you see this GIF, in order to make, so this is the initial, actually, yeah. So this is the initial image that you want to be transposed to a second image. In order to make the initial image be at the same, so to be the same size as the result, so the result of applying a convolution, you also need to add some padding, because if you're not going to do that, your final convolution, your final result would be smaller than the initial one. So basically, when you say borders same, you're saying after you've applied the convolution, I expect to have the same size of, so the images, resulting images, I expect them to be the same size. Whereas if I would say I want valid convolutions, basically that says I don't care about padding. I don't care that the image would shrink in time by applying the convolution. Just give me the correct output of the convolution. Usually you would use same. So usually you would say that you want the same value because it makes life easier and it makes everything more manageable, like when you design a model. I just showed you before an example where I mentioned that the last thing that we were doing, like the dense layer, isn't that important. I was just telling you that that's just a way to say I want 10 values. Well, actually I was a bit misleading on that front. It's actually doing something. It has some weights, so it's actually learning something for you, and it defeats the purpose of a convolution to some extent of using dense layers. So there's a way around that. There's a way of only using convolutions, and that makes the model learn so many more features and more correct features, because you're not trying. What happens when you do flatten, and then you do a dense layer on top of it? Basically you take an image and you unravel it, and you destroy the speciality of it. So the speciality of it. Maybe I didn't pronounce that correctly. So you take an image which is like a matrix, and where each pixel, a neighboring pixel, has some meaning for each neighbors, and you're unraveling it into a long line of values, and then on top of that, you're applying linear regression. At that moment in time when you're applying linear regression, you're not viewing it as an image, so your filters, all those filters, nice edges, edge detectors, kernels that you just learned before, those are not interesting anymore, or at least they're not as interesting. So what you need to do is to not do a flatten. And one way of doing it is saying, okay, at my last layer, I want 10 filters, and I want I want to be looking at the whole picture. So I want to be looking at the full image and give me valid results. Don't do any padding. I want just, if the result is only 1, I want that 1. I want that number. So when you compile this model, you get this shape. So you have 28 by 28 and 7 filters. Then again 28 by 28 and 7 filters because you have same border mode. And then at the end, you're saying, okay, each filter, each of the 10 filters, I want 10 filters that represent one of my possible value, one of my 10 possible values. So those 10 filters, I allow them to look at the full image, and I expect to have only one number. And then you do flatten. Basically, you don't care at this point. They're not images anymore. They're just representations. And then this is your model, right? It works. It takes a lot more time to train because you only have convolutions, and the dense part was hiding some of the complexity for you. It was finding ways of combining features, but it's more correct. It's more inspectable. If you now look at the features found, like the kernels found in these convolutions, you found them to be more interesting, to be more accurate, to tell you more about the world. But again, it's harder to train. It takes longer, and it has more errors than the convolutional model that ends with a dense layer. Let me talk about, so we've talked about convolutions, and maybe they seem to you like there's only one piece of a puzzle, so they're not useful by themselves. And actually, we have a pretty good model, which is VGG16, that won the ImageNet competition in 2014, which is mainly composed, actually, yeah, I could say that it's only composed from convolutions. And to prove my point, this is the VGG. I just implemented VGG for you. I mean, it's taken from somewhere. It's not that difficult to implement, but still, I didn't write this by hand. So what you're seeing, besides these zero padding stuff, which basically say border mode is same, and besides max pooling, so if we ignore these max pooling and zero paddings, which don't do much, they're not learning anything, they're just restricting the network to be smaller and adding some zero values on the edges, there's only convolutions. So you have only convolution, 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 convolution. And at the last stage, you have a fully connected layer. Unfortunately, so maybe that wasn't the best choice for them, but it worked. So VGG won the competition. So what does it mean? It means that if you understand convolutions and if you know how to use them, at this point, you can do state-of-the-art machine learning. Or you can do state-of-the-art machine learning as they were in 2014. Of course, things have moved beyond that since, but it's not that far away. Another interesting aspect of convolutions is that they're invariant to size. So what I mean by this is that because the kernel is a fixed size kernel and it scans the image from left to right, it doesn't care really if your image is 28 by 28 or if it's 2000, I don't know, by what, 2000 by 2000. It's doing a scan, and it's generating an image from your input image. So what this means is that if I try to enlarge my images, if I try to say, okay, take those 28 by 28 images and convert them to 200 by 200 by some interpolation method, and I have a new data set, I can basically say, okay, take the layers from the last model, take all the features that were learned from the smaller one, and use them directly on my new model. So I'm transforming the things that I've learned on a small scale. I'm taking that and using that on larger images, and this works. Of course, we now have approximately 3 million parameters if we do this, because the last dense layer would add so much complexity. But the two layers that we reuse are the same, exactly same weights, exactly the same logic. And if we try to fit it now, yeah, it's not, you can't really see it. But so it's progressing, but it's progressing at a much lower pace. And results are not, they're good, but not outstanding. If I would let that, and this is to be understand. So this is this is understandable because there's like 3 million parameters. So you have to be able to fit 3 million parameters correctly before you want correct predictions. And we don't have that much time. Or we're not using the same amount of data because we only used 10,000 examples compared to 60,000 examples at the first training, the small training. Okay? And if you're wondering if convolutions are only applicable to images or two-dimensional stuff, you would be wrong because there's variance for convolution for one-dimensional convolution, and there's variance for three-dimensional convolutions. And when I say one dimension, I mean like sequences, like texts and time series. So one way of doing time series training is to use a recurrent neural network. But turns out recently that convolutions are actually a better fit for modeling sequences and interactions in time. So this is, for example, a convolution applied, a one-dimensional convolution, because you have the dimension. One word is a single value. So this is a convolution applied on two consecutive words. So this is the stride of two, let's say, because it looks at two words. And a convolution, basically, the next layer would say, okay, I see two words at a time. I see the actual, and then actual service, and then service was. And I'm pretty sure that at Facebook they use this approach. They use convolutions for modeling text instead of using recurrent neural networks. The 3D convolutions can be used on video because you now have sequences in time, so you have 3 dimensions. You have images, like two-dimensional images, and you have them in a sequence. Okay, so yeah, basically this is my full talk. I guess it's a lot of information to take at once, but I hope that you at least understood some part of it. And if you have any questions, I would be glad to answer them. Thank you.